Hi, everyone. Good afternoon. So this is going to be one of those talks where I'm not actually going to talk that much about Bitcoin, and I'm really going to dive quite deep into data centers and energy usage. But I will cover the role that Bitcoin mining has to play. And this is one of the areas that I'm looking at as part of my work within KPMG right now. So a little bit about me. My QR code for LinkedIn, for if anyone wants to get in contact with me and talk to me about my work. I'm the Cloud Innovation Lead at KPMG UK. I focus on the intersection of cloud with other technologies, Bitcoin being one of them, other technologies such as IoT, AI. And the area that I'm looking at, and the area of this talk today, is around energy optimization within data centers. The other areas of Bitcoin that I'm quite interested in are risk management in Bitcoin mining. I was the author of a paper that KPMG put out on this subject late last year. And I'm also quite interested in financialization of hash rate via derivatives and corporate adoption of Bitcoin. So, to begin, an analogy. Many of you would have heard this analogy before. Anyone can build a bridge that stands, but it takes an engineer to build a bridge that barely stands. And what this actually refers to is how do you use your resources in an efficient way to make sure that you don't over-engineer something. Using the bridge as an analogy, you could easily build something that uses huge amounts of concrete and steel, but is it fit for purpose? Is it massively over-engineered? Is it built too heavily for the load that it's going to take? Now, what we're quite interested in is how does this concept apply to data centers? So if we look at the design principles of what a data center actually has to do, performance, reliability, scalability, energy efficiency, security, and maintainability, these are the core components of what a data center should do. When we talk about high performance, we're talking about compute capacity, memory capacity, storage, everything that's needed for modern AI workloads. When we talk about reliability, this could be at the rack level, it could be at the site level. It's all about making sure that your critical workloads never go down. Scalability, anyone that's familiar with orchestration platforms such as Kubernetes, you understand the way these platforms scale workloads up and down, and that's a core component of AI. Energy efficiency. As more and more CPUs are being released by various vendors and GPUs as well, there's a big drive to how many flops per joule, for example, can be provisioned by these devices. Security, we talk about cybersecurity, whether that's firewalls, networking, there's physical security as well. And finally, maintainability. You need to be able to run the thing without it being massively complicated. So the components that go into the data center, there's the compute infrastructure. So we talk about the CPUs, GPUs, networking, storage. When we talk about cooling systems, there's some great expos here today talking about liquid cooling systems and how they apply to Bitcoin mining. Data centers have been using these types of technologies for quite a while. Power is obviously a critical component. You can't have your power supply suddenly disappearing for your data center. It would take out your critical workloads, and therefore there's a big drive towards having redundant power sources going into your DC, using UPSs, uninterruptible power supplies, using generators, and a huge amount of management and monitoring goes into actually making sure this stuff continues to function. At the compute level, there's also monitoring around what's going on with regards to your compute clusters to make sure your workloads are continually running. And then finally, as I mentioned, there's the security aspect of it, which is the physical and the cybersecurity itself. So what do you need to consider when you're actually building a data center? So it needs to be modular. Now, when we say modular, what do we mean? If you're building a data center rack by rack, you need to be able to replicate that design from one rack to another. It needs to be modular. It needs to scale. So as and when you're plugging in more modules, as your workloads scale up and down, you need to make sure that's relatively straightforward to do. Again, energy efficiency, making sure that you're using as little energy as possible, making it sustainable. So there's a big drive right now towards ESG and ESG considerations about your data center. And then obviously flexibility. The demands of what's happening inside data centers have massively changed over the last few years with the proliferation of generative AI systems. And the data centers that haven't been able to adapt have been swamped, and they're really struggling to provision their workloads. So how does this actually relate to energy consumption? Where there's two types of energy profile consumptions of what you can use. So we refer to them as firm load and flexible load. A firm load is something that requires consistent electricity demand. So if you think of traditional data centers, they've always needed a steady input of energy going into them. You can't have massive fluctuations of energy going into your data center because otherwise you'd end up in a scenario where you have to kill critical workloads and it causes problems. So you need to have the guaranteed supply, it needs to be predictable, but it's at a higher cost. When you've got flexible loading, what that refers to is how the energy consumption can be shifted as you're consuming it. So we all know with Bitcoin mining, for example, it's very easy to shut miners down and therefore it's quite adaptable with the way it uses energy. That would be a really good flexible load. However, there is lower cost associated with it, but there's obviously less guarantee around the availability of the workload that you're running. So if we're now going to look at what you can actually do to minimize your power consumption, you have to take into account the type of workload that you're talking about. So here we're talking about if we assume that data centers are firm loads, which they are because they're critical, you need to be very careful about how you orchestrate those workloads to optimize your energy usage. We're starting off with something as basic as just identifying your critical and non-critical workloads. Anyone that's run a data center before will know all about the dev environments and pre-prod environments. They're the ones that usually get killed when you have constraints around capacity or energy. So prioritization is critical. How you manage SLAs and how you manage your workloads, that's critical. The technical challenges that introduces is how you're allocating resources to different areas. So how you're allocating resources to different workloads of different criticality and making sure they continue to run. Using virtualization, containerization, so VMware, Kubernetes, these are critical components to take you on this path, as is the flexibility of cloud. Being a cloud person myself, obviously, this is something that I'm quite keen on. It does introduce operational challenges when you talk about orchestration of workloads. What it does is, if you're bringing workloads down and you're bringing them up depending on what's happening with your energy usage, there has to be very clear communication to the people within the consumers of your applications inside your business, which leads into very, very strict concerns around monitoring and reporting. There's obviously the issue around business impact. You can't have applications coming down because there's an energy shortage in your data center if it's one of your key revenue-generating applications. So for example, if it's your front end of your website where all your customers are going in and processing all their payment data, or the payments are being processed, you can't have that coming down. That will just cause massive problems for your company. It will lead to massive customer dissatisfaction, and with how quickly things like this spread over X these days, within half an hour, half the world will know about the outages that you're having, so you have to be very careful. There's the ethical considerations around fairness as well, which is how do you make sure that you're not disadvantaging certain users over others? And this is the ethical conundrum that we have to deal with. So if we jump forward now to what's happening with AI models, what we've actually been talking about is consumption profiles and curtailment profiles of different applications. Now, with AI models, there's two types. There's two modes in which they all run. There's inference mode and there's training mode. Training mode is when obviously the model is actually training and processing all the information. For people that understand the way neural networks work, you'll know that that involves forward and backward passes through the data. It's very consistent demand from the energy, but you can't kill it. You can't curtail it. It needs to be allowed to run. Inference mode, on the other hand, has a lower baseline, but is very spiky. So these two types of workloads have very different profiles. And what this ultimately leads to is different curtailment strategies and how you can optimize energy usage. So if we look at inferencing specifically, when you send a request through to ChatGPT, for example, or Gemini or any of the LLMs, what you're actually doing is sending an inferencing request through to the model. It's when you're sending a query to pre-trained data and generating a response back. That by its nature is very asynchronous, and that means that you're going to have these fluctuations in compute demands and energy usage. What it means is when you have inference as a service provider, so ChatGPT is an IaaS provider, you're using pre-trained models and you're not using the infrastructure. You're actually just consuming the service. It's massively beneficial because you don't have to deploy the model yourself, and you just consume the model via an API access. What this also leads into is GPU as a service, because if you're now curtailing the AI workload based on how often it's being used, so you're not provisioning a huge amount of compute resources. Why would you provision the GPU resources that's required to process the workload? Why would you not also scale that down? So what you now end up with is you use GPU as a service providers, and you actually start curtailing them using these different types of solutions. So what you do is you actually monitor what your GPUs and your CPUs are doing with regards to how many flops they're actually consuming, how much energy is actually being used, and you start to adjust them dynamically. You start to use frequency scaling on your GPUs, you start to use voltage scaling, and you also use activation and idling. So what this means is, as GPU workloads are going up and down, you can adjust the clock speed on them to determine how fast they're running. You have voltage scaling on them as well to determine the intensity of what they can do. And then finally, deactivation. If a GPU isn't under load, why would you have it running? Why would you not bring it down to the floor that you can do this? Where this gets quite interesting is using adaptive thresholds, because as your demands in your data center change, what you need to do is pay attention to these thresholds where you're switching things on and off, because these thresholds are never going to be static. They're going to be constantly evolving as your workloads evolve. So what are the benefits of curtailing GPUs? So you're reducing your energy consumption. Because you're using less energy, you're driving efficiency. You're putting less strain through your GPUs, therefore you're extending their lifespan and having cost savings. But there are considerations that you have to take into account. You need to make sure this doesn't happen in a way which impacts your workloads, and you need to make sure that it's done in a way that your workloads are correctly characterized and profiled so you know which ones they're going to. And again, coming back to the example of techniques, voltage and frequency scaling, power capping, and using sleep states. Now, what happens with the energy that you actually save by implementing a strategy like this? When you design a data center, what you do is you'll provision a certain amount of energy which will go into your data center. So you'll have a power purchase agreement with one of your suppliers, and this will then dictate how many watts are available to you in your data center. If you're now reducing the amount of energy that you're consuming, this is energy that you've saved, but you actually need to do something with it. This energy, you can't, if you just discharge it in your data center, then the question is, well, why didn't you just use it to provision compute resources? So you have to do something with it. And the answers has always typically been use on-premise batteries. So battery storage within your data centers are great, but the problem is you have the cost to maintain them, and then they run down over their lifetime, and it's huge upfront capex required to do so. The other advantage with having a power agreement is you can actually sell the energy back to the grid under a sellback clause within your purchase agreement. This will be dependent on the demand coming from the grid and to determine whether it's worthwhile or not. So what you actually need is a buyer of last resort, someone that creates a price floor for your energy. So if you do run this type of strategy in your data center and you save a lot of energy by using these various curtailment strategies that I've just described and using workload characterization as I've spoken about, there needs to be a price floor at which you can say, okay, someone's going to step in and buy this energy from me. And this is where Bitcoin mining steps in. So we all know with Bitcoin mining, it's often referred to as a buyer of last resort because it can just consume energy that's otherwise unused. And what you can do is actually use Bitcoin's features and the way it consumes energy to perfectly complement this type of strategy within a data center. So using the energy intensivity of proof of work, you can make sure all the energy is consumed and monetized. Miners are very flexible, so they can go to any location and integrate in. They are a buyer of last resort, and it's driving energy adoption. What this ultimately leads to is some thinking around what a future of a data center may look like. So in this type of design of what a data center could look like, in this context, IaaS is inference as a service, not infrastructure as a service. But what you essentially have is your inferencing requests are coming into your data center, and your resource manager is actually looking to see, okay, how much compute capacity do I currently have available? Does it match with the workloads that I'm trying to run? If not, I need to bring more devices up and down. So that could be more nodes in your containerization cluster. That could be more GPUs that are currently idling or have voltages turned down. When these additional devices get brought online, you now have the scenario where you can move workloads around using a container orchestration platform such as Kubernetes, for example. So you have your two levels of orchestration at the device layer and at the workload layer. But as you start to move these things around, what you can also do, because if you're using GPU and CPU idling and curtailment, is you can actually have a context switch going on inside your data center where you're diverting energy from your GPUs to your Bitcoin miners. And what this ultimately leads to is you create a very constant energy supply, energy consumption profile from your data center, despite the fact you have wild fluctuations of what's actually going on inside your DC. Bitcoin miners are great for this, but they're not as fast as they need to be to do this. So you still actually need some type of on-premise battery system. And this is where we talk about the two different types of battery energy storage, fast access versus slow access. Your fast access will typically be your high-performance capacitors, which will quickly allow discharge as these devices are being scaled up and down. And your slow access batteries will typically be your UPS supplies or your general-purpose batteries. What you also have at the top is the various signals coming in from the grid. So you've got your energy supply coming into your data center from the grid, and then you're monitoring the price signals coming from the grid, the demand. If the energy supply or the energy consumption in your data center drops to a certain point where you're now monetizing via Bitcoin instead of GPU provisioning for your AI workloads, you can then monitor the price signal coming from the grid to say, okay, is it more profitable for me to currently mine Bitcoin, or is it more profitable for me to currently sell this energy back to the grid? If the signal coming from the grid is higher than the price point at which you're monetizing Bitcoin via mining, it makes more sense to sell back to the grid. And this is where you end up with this four-way equilibrium between these different systems. You have your GPUs, you have your Bitcoin miners, you have your on-premise batteries, and you have your sell back to your grid. So how does this, there's a few different ways this can work. One we refer to behind the meter versus in front of the meter. Behind the meter is where you have co-location, so it's co-location of energy production and Bitcoin mining in data centers, whereas in front of the meter is where you have power agreements and it's metered connections. There's pros and cons to either approach. It really depends on the scale at which you're consuming energy. But this also leads down the road of, regardless of which way you go, you have to use very careful energy management, and there's certain optimization strategies that you have to consider. So is co-location of energy producers and Bitcoin mining the optimum solution? Based on the blueprint that I put up on screen earlier, I would say that this is the way to go. But there's a lot of work that needs to be done from an infrastructure point of view, because each of these types of producers, whether they're energy producers, whether they're HPC producers or Bitcoin miners, they have different infrastructure needs for what's actually needed within their sites. And trying to design sites which covers all three of these scenarios is going to be challenging. But if done correctly, you can monetize your energy in the most efficient and optimum way. And what's the end goal? What is it we're trying to get to? So we're trying to get to a data center which runs with as lean as possible, using as little energy as possible and making it as efficient as possible. So you do that using a combination of on-site production, GPU curtailment strategies, energy management strategies, incorporate Bitcoin mining into it, and this just will help you drive reliability and stability of your workloads. So what we end up with is the data center that barely runs. So if you come think back to the analogy that I used at the start of my talk, where I spoke about the bridge that barely stands, this is why I use that analogy to begin with, because if you go down the route of this design and follow this through to its logical conclusion, what you end up with is a data center that uses as little energy as possible and is never over-provisioned. So coming back to the analogy of a bridge that barely stands. I've probably rattled through that a bit faster than I was expecting to, but I hope that gave you some thoughts around some of the work we're doing in this space and some of the areas where Bitcoin mining and HPC can come together. I will be around if anyone wants to ask me questions about any of that. But yeah, thank you for listening. Hope you enjoyed that. Cheers. Thank you.
Secure your BTC Prague 2026 ticket at the lowest possible price now.